partnership with the Texas Advanced Computing Center, or TAC. So we have access to some of the world's most powerful supercomputers and computing resources in general, which we've certainly utilized in the past. And then really what we do is we develop and maintain state-of-the-art software platforms, really to support clients. So this has a variety of different things, things for insurance, deep sea vision AI, blastFoam is part of this. And we also work with some other commercial as well as federal clients, really doing some pretty cool applied research projects. So who is specifically working on blastFoam? As I said, I have been the lead developer of the blastFoam solver. I got my PhD from Iowa State in mechanical engineering in October. My area of expertise, if you will, has primarily been multi-phase CFD, specifically quadrature-based moment methods. However, I've kind of dabbled in a lot of other stuff as well, from compressible flows, so what we're doing now, a little bit with reactions, some combustion, that kind of stuff. Next, we have Peter. So Peter did the initial development of blastFoam, and I was kind of brought in to expand upon that. So he does a lot of general CFD as well as CAD integrated tools for simulation-driven design. He also does a lot of the applied R&D for our clients. And he's also developed some of the risk assessment software that we use, and that is used in combination with blastFoam. And lastly, we have Tim Brewer. So Tim was the one who was supposed to be speaking today. He was a technical Army officer for about 18 years. So he's got a lot of experience with testing and modeling and simulation experience, specifically for weapon development and effectiveness, as well as protective designs. He is an analytic consultant and DHS safety act accredited assessor for infrastructure and buildings and venues. He is also a professionally licensed engineer. Okay, so here are just some quick examples of what blastFoam can be used for. This is specifically for blasts, obviously. So the first one here, we have basically a DNS type simulation. It's 2D, so it's not 100% correct, but you can see we have Taylor-Richtmeyer instabilities, those little kind of vortices, if you will, forming on the edge of the shell. Then we move on to a blast wall, where we have a more complex geometry behind this wall and looking at the loading on it. blastFoam has also been used for structural analysis. So looking again at the loads, most of what we're going to be looking at is impulses and pressures on structures. So looking at the loading and how likely it is to be negatively impacted. And then lastly, we have a cityscape calculation. So these are based on some of the current insurance calculations we're doing, looking at damage to buildings and things like that. Okay, so today's a little bit of today's overview. So kind of go through a little bit of the background on blastFoam, kind of where we started, where we're going, what the plans are. Go very briefly through some of the solved equations, a little bit of blast theory, just because it's probably not normal for everyone. Then we're going to go through the structure of blastFoam, just kind of briefly walk through the code, how it's structured, where you can find things. Then we'll talk about some additional features that aren't exactly core to blastFoam, but can be used hopefully by most people, regardless of your code, or what solver you're using, sorry. And then we'll walk through running a simple validation case, and then we'll go through some additional validation cases, basically just show the code validation, and then future work as well. Okay, so what is the reason for developing blastFoam? As you can imagine, there are not really any unrestricted free or open source codes that are capable of performing blast modeling. Generally speaking, these commercial codes either are very expensive or they're very restricted or both. So it's very hard for people getting into the field to really be able to use these. So what we wanted to do is we wanted to create an unrestricted version of this that everyone can use. It's easy to validate. You can run all the validation yourself, and really help people starting off in research, or so you don't have to create your own codes from scratch. So obviously OpenFoam is extremely extensible, which was very attractive for us. It's very widely used already in academia, industry, research, pretty much everywhere, arguably one of the top 3 CFD codes in the world. And really the ability for us to focus on the physics instead of the programming was a major upsell. This scalability allowed us to really focus on implementing the blast specific things that we wanted that were novel, without having to duplicate a lot of that background work. Okay, so kind of the roadmap of blastFoam, so the timeline, if you will. So originally, blastFoam was presented at the OpenFoam Users Conference in Germany and the United States in 2016, 2017. So that was Peter's work. It was a very bare bones solver, really designed specifically to solve one equation. It had a set equations of state. And then, so I came on in October and we released blastFoam 2, the public release, in, I believe it was November. So it was kind of just a little bit of improvement, some more runtime selectable stuff like the equations of state, incorporation of the standard OpenFoam adaptive mesh refinement, things like that. Then in March, we released blastFoam 3. So this was a much bigger change. A lot of refactoring behind the scenes, added turbulence models, the standard OpenFoam turbulence models, some simple reaction models, radiation, additional equations of state, as well as some other models. So blastFoam 3.5 will be released later today. It's basically just includes some additional improvements to the thermodynamic structure, as well as incorporation of adaptive mesh refinement from Rettenmeier 2019, and I'll talk about that in a little bit. We also have some new function objects specific for blast, and then a new blast multi-region solver. Looking forward, we will be releasing blastFoam 4 in late summer, early fall. And this will really have a focus on particles. So this will include things like 2 or multi-fluid models. So this is the Euler-Euler type method, similar to reacting Euler foam, obviously with a compressible, from the compressible version now. Also looking for Lagrangian solvers, as well as coupling with OpenQBMM, which is what I have done a lot of work on in the past. And then looking forward, even further than that, way down the road, we have blastFoam GPU in the works, which is essentially going to be just a very performance-driven blastFoam. So really focusing on that performance and not so much the extensibility or anything like that. All right, so just gonna very briefly go through the governing equations, a little bit on the model problem that we use. So the governing equations we solve, they're the standard compressible Navier-Stokes equation for single phase. So this first line here is gonna be the standard compressible Navier-Stokes equation, where we also have the addition of species transport, which is Y. That's specifically for one of our additional solvers. When we move on to either the 2 or multi-fluid model, or multi-phase model, I should say, we have additional volume fractions and phase masses that we need to transport. So basically, these all break down to the standard mass, momentum, and energy conservation equations. In addition to the standard hyperbolic fluxes, we also have these additional source terms. specifically for momentum and energy, where we have this momentum source here, which is essentially contributing to or drag, which will be used later, specifically for particles. The energy source here adds energy for things like detonation events. And then we have our viscous source terms, which are the standard Newtonian viscous stress tensors. Okay, so the model problem. So this is a very simplified version, and we do have a couple different options, and I'll talk about those in a second. But this is kind of the simplest. So basically, what we do is we assume that we're initiating our detonation at a single point. And then from that point, we have a detonation wave that propagates outward at a specified detonation velocity. And this, again, can be changed based on our activation model. I'll talk about that in a second. And this detonation velocity is very, very easy to find, especially for most common high explosives. And this is for the solid phase, that the speed at which that wave propagates through your solid material. So the reason why we use this very simplified model and assume basically an infinitely fast reaction kinetic with zero length. The reaction zone, which you can see here in the image between the products and the reactants, where all of this is occurring, is on the order of 1/10 of a millimeter to 1/2 of a millimeter, which for most practical things is much too small. Unless you're doing an actual DNS calculation, it just doesn't make sense. So for things like normal large-scale engineering calculations, the simplified model does a fantastic job, and you really don't see much difference with some of the more complex models. So the reactants are a solid phase, essentially, and you're looking at how that reacts to produce these product gases. So the transition between these two states is essentially governed by a reaction progress variable. And the reactants can be described by a varying number of equation of states or materials. However, in general, we blend the two states. So here you can see for pressure, we have this lambda, which is the reaction progress variable, or how reacted an individual cell is. So for this model, it's either 0 or 1. It's 0 if the wave has not passed, it's 1 if it is. And then we blend the pressure of the products, which is this PJWL, and then this P reference, which is going to be your solid pressure, and that'll give you your total pressure. So the product gases, generally speaking, are described by the Jones-Wilkins-Lee equation of state. So this is very standard. And the JWL is a very, very well-established equation of state for energetic materials. And because it's so well-established, most of the coefficients for many materials are commonly available. You can see down here the final form of the equation of state. So you have a couple coefficients. You have this omega, A, B, R1, and R2, as well as a reference density, which is part of this V term here. And these vary depending on what material you're using. So they're different for TNT or C4 or different things like that. And then for the surrounding fluid, we typically use air. This can change and really has no effect on the actual detonation event. It's just how energy is transferred to the surrounding fluid. So generally speaking, we use an ideal gas. However, it's not required, and there are other options. Okay, so all of this that I just kind of talked about is lumped into what we call in blastFoam the detonation model. So what the detonation model does is it handles the transition between the solid reactants and the gaseous products. So the transition between these two is determined based on the activation model. So what I was just talking about, where it propagates at a linear or at a detonation velocity, is called the linear activation model. A more simplified version even than that is none, which basically means that when you start your simulation, all of the energy is immediately released and it expands from there. The more complicated ones are the pressure and Arrhenius rate versions. So the pressure-based, it allows, as the pressure increases, you begin to activate, and your activation rate is dependent upon the local pressure and the coefficients you specify. And the Arrhenius rate is then temperature dependent, but follows the same thing. And then lastly, so it wasn't discussed previously, however, similar to an activation model, but also in addition, are afterburn models. And what these are they essentially are a way to add additional energy due to reactions that are occurring after the primary detonation event. And there are a couple options. There's either the Miller, which is very similar to the pressure-based activation model, or a linear release rate. You can also turn it off if you want. Okay, so as I mentioned, that blending for pressure, it's done for every variable, every thermodynamic variable for this detonating phase, if you will, where we're looking for a given quantity and we want to blend the reacted and the unreacted states. Lambda here is the reaction progress variable. Typically, the exponent here is 1, but you can use other exponents. And then, so we have an evolution equation for the reaction progress variable. So we have our time derivative, we have advection in space, and then we also have this R dot, which is going to be your reaction rate. So this is determined by your model of choice. It'll vary between linear. Basically, if you don't use any, this R dot is 1 or 1 over your time step at the first step, and then it's 0 from then on. However, we add energy based on the time rate of change of lambda. So this is a more physical way to add energy into the system. And the energy we add is determined by this E naught here, which is going to be the detonation pressure, if you will. It's given in units of pressure, which is why it's divided by rho naught. And the afterburn model will use basically the same equations. However, R dot and E naught will be different. They'll basically just be different values or different models. But then this energy source here is added to the conservation of energy, which adds energy to the system. So in order to use this detonation model, we need to fully define both states. So in order to do that, you have to specify your equation of state, and the equation of states will be the kind of the primary focus, thermodynamically speaking, of this. So for reactants, we have a couple options. So if you really don't know anything about the solid properties of your material, an ideal gas will work. It's not recommended if you plan on using something more, I guess, advanced. But for things like the linear release rate, linear activation model or no activation model, it really doesn't affect anything because your wave propagation speed should be faster than the speed at which your solid is moving. However, if you do know some things or you want to use one of the more complex activation models, such as the pressure-based or Arrhenius rate, I would suggest using a solid equation of state. So this would be things like a Murnaghan equation of state. The Birch-Murnaghan, we have a second and third order, or we also have a solid JWL. And then for products, currently we have 2. We have a JWL and an LSZK. We have other BKW. The BKW model is a temperature-dependent product model as well, but it's currently being tested. So all of these are then used in combination with your activation model, which you specify, and the afterburn model, which you specify. All right, so now we're gonna kind of just walk through the structure of the code a little bit. So if you have any specific questions on like where things are, hopefully this will help a little bit. I know we had some people asking about where exactly specifically things are done in the past. It's kind of convoluted in that sense, but hopefully this will kind of explain that. So one major difference between blastFoam and standard OpenFoam is that we use explicit fluxes for everything, with the exception of viscosity. That's handled separately and is just done as a substep, basically. But basically, because we use explicit fluxes, it allows us to use a multi-step ODE approach. So because of that, we have implemented a time integration system. And basically what this is it allows a runtime selectable ODE solver to be used. So basically what this system will do, this is kind of just a very basic system. It'll step and integrate each system. And basically in order to, the way that these systems are integrated are determined by your different things, which I'll talk about later. But basically, you're given a step number and the butcher table coefficients, and then the systems are integrated. It's very easy to just derive new systems. These systems are things like your total Navier-Stokes equations, basically. So your mass, momentum, and energy conservations. But in order to do these, you have to update, you have to solve, and then you have to clear. And clearing is basically just a way to save space and storage and sending buffer size, basically. So currently, we have Euler, RK2, RK2 SSP, RK3 SSP, RK4, and RK4 SSP. It's very easy to add new systems or new ODE integration schemes. And then the scheme which you use is specified in the FE schemes. And I'll show where that's specified later when we go through the case. Okay, next we have the thermodynamics. So this is the thermodynamic library in blastFoam. It's specified under the thermodynamic models and the SRC. Basically, as blastFoam has evolved, it's become much more similar to the standard OpenFoam thermodynamics. So this means that we have a species, an equation of state, a thermodynamic model, and a transport model. The major differences between what we have and what OpenFoam typically has, we are density based. So that means we use a known density to find our pressure and not the other way around, like is typically done in OpenFoam. Another thing is we can either use an internal energy or temperature-based equations of state. So we allow the option to do either. As the user, you don't really have to deal with this. It's kind of handled naturally, handled behind the scenes, but it is possible. And currently, we do not have mixtures or reactions specifically implemented in blastFoam. I'll talk about sort of a way around that. But basically the reason for this is because the primary focus specifically for blasts was on multiple equations of state and not so much for multi-species. So you can't really add equations of state when they're not the same. However, we would like to work on this in the future. So hopefully that will be something that is added eventually. Okay. So the equations of state we currently have. So this has been really the primary thermodynamic section of blastFoam other than that detonation model, which I mentioned. So the Micronizing form of the equations of state is the internal energy based versions. So these are definitely preferred for compressible flows just because it's a known variable. You don't have to derive it like temperature. So these are definitely preferred. So things like the ideal gas, stiffened gas, Tate, van der Waals, GAWL, Cochran-Chan, LSZK, and Dewan-Nickel. So basically all of these equations of state, they have an ideal gas contribution, and then they have like a deviation from ideal gas, which is what the micronizin form is. So the Dewan nickel is still experimental. However, it is very close. What it is, it's basically a real gas equation of state. It handles dissociations of ions at very, very high pressures and temperatures. However, it's still currently in the works, or still validating it. It's kind of hard to validate these just because they break the standard shock tube problems, or at least the high pressure and temperature ones. So then next we have the temperature-based models. So these are either pretty much experimental or solids. So the BKW is a common energetic material equation of state that is based on temperature. Still currently validating this. And then the BWR is typically used for things like vapors or condensation, I believe, or cavitation. And again, this is still experimental. And then we have our solid equations of state, which are the Murnaghan and the second and third order Birch-Murnaghan. And then lastly, so separate basically from both of those, we have a tabulated equation of state. So this tabulated equation of state uses a very general formulation. So basically you can provide any table for pressure and temperature, and it'll do the lookups and return your pressure and temperature. One thing, both of these have to be, the coordinates have to be density and internal energy. There is currently a tutorial if you're interested in this. It's shock tube tabulated. Basically, all it is, it's a tabulated equation of state that uses an ideal gas and constant CV values to build these tables. So if you have things, if you have real gas equations of state, or tabulated equations of state for a fluid that's cavitating, this is what you would want to use. And it's been very well validated. Okay, so after that, we have kind of a higher level of the thermo model. So we have a couple layers here. We have the basic thermo model, and then we have an E-thermo or blended thermo model. And then finally, we have either a fluid thermo or a solid thermo. So again, this is very similar to the standard open foam thermodynamic models. We have both single phase and multi-phase versions of this. And then within those, we have runtime selectable phases, if you will. So this is basically, you can choose each phase, either a basic fluid phase or a detonating fluid phase. So the basic fluid phase is essentially just a normal gas or normal liquid. It's not detonating. And then the detonating fluid includes that activation model. It's blended, so you have the solid and reacted state, and then you also have that afterburn. So if you want to be simulating something like TNT, your TNT would be that detonating fluid. And then next we have the solid material or solid model. Basically, it's only used for the multi-region. However, they are there. And they'll be used in future releases as well. And then, so what all of this does is it uses the thermodynamic model specified previously. And for multi-phase, it also handles the calculation of shared thermodynamic variables. So basically it blends, if you will, it's not exactly blending, the pressure and speed of sound of multiple phases, so that you get a single shared pressure and speed of sound. All right, so next, so the main compressible part basically is done in the compressible system. So hopefully the time integration system makes a little bit more sense after this. So basically it's derived from that, and this is each substep of the ODE solver is done in the compressible system. So this system, it stores the ODE fields. So that means it stores like old values of mass, momentum, and energy, as well as the changes in mass, momentum, and energy. It's set up to only solve the ones that you need. So if you do an RK2 with no required storage, it won't create those extra fields. And then it's also responsible for the conversion between primitive and conservative variables. And by that, I mean mass, momentum, and energy. And the primitive, so those are the conservative variables. And then your primitive variables would be density, velocity, pressure, and internal energy. So the basic blastFoam solver assumes that you have a single shared velocity and single internal energy. So this is generally called a 5 equation of state. And then, so as I mentioned before, we can have multiple phases. And again, that's handled in compressible systems. And it's the number of phases that you use is determined by a list of phases that you provide. So all of that's handled automatically. You just tell it how many phases you want, and it'll create the correct system and thermodynamic model for that. And then as of blastFoam 3, we also have the option to include turbulence models. So if the viscosity is 0, you don't have to worry about this at all. It's not created. However, if you do, it'll require that additional turbulence properties dictionary, and it'll create the turbulence model that you want. And then lastly, we have the option to include radiation models. So different than normal open foam, we use an explicit method. Again, this is just because of the fluxes, basically. The actual solving of the radiation model is standard. So if you do an FE DON, it'll still solve that using the matrix operations, but the actual addition of energy into the system is done explicitly. If for whatever reason the global time stepping causes your radiation to become unstable, you can also use an ODE solver. So it's a very simple ODE solver, which basically just relaxes that energy at a rate, or by subtime stepping, sorry. And currently we have a limited selection of absorption models just because they're still being ported to blastFoam thermodynamics. All right, next we have the flux schemes. So these are arguably the most important part from a numerics point of view of the compressible flows. So currently we have HLL, HLLC, AUSM+, and then the standard open foam Kurganov and Tadmor schemes. So these have been really separated from the other classes I've presented. So if you want to use these in something else you're doing, you certainly can. Basically, you just pass it your fields and it'll return the fluxes. So another nice thing about the explicit fluxes is that we can use higher order interpolation without the added cost of the expensive matrix high order solutions. So this allows for stable solutions by using limiters and that cubic interpolation without that extra cost, which is really nice. And actually, I've found that it actually can be more stable with the higher order interpolation, which is weird, but that's just personal experience. So using these, we also have a new Riemann flux scheme. And basically what this does is it makes use of the explicit fluxes. And it replaces the implicit FEM divergence term, which you typically find to make advection stable or more stable. And it replaces it with high order fluxes. So this makes advection explicit for other variables. So for all the conservative variables, this is just done. However, for things which you have a transport equation for, you can use this scheme to allow for higher order interpolation. However, you still have those limiters, so you can handle the shocks better. One note on this, there are poor results when you have large implicit source terms. So this is, for example, for turbulence models, you have these large implicit source terms, and basically what happens is because you're dividing by a very large number, it basically ends up canceling out the advection, which is not what you want. So for that reason, turbulence model should still use the normal advection schemes, at least for now. Hopefully it'll be something we get done in the future, but as of right now, it's not. Okay, so then that was kind of just a very brief walkthrough of the core code, kind of the numerics behind it, the sort of underlying physics. So this section will primarily be on some of the additional features we've added, mostly just for user friendliness, easier calculations of things, stuff like that. So I would say the biggest additional feature here is the use of the adaptive mesh refinement from Rettenmeier et al. 2019. So this is the link to the GitHub repository. So what this is it is a adaptive mesh refinement that has 2D axisymmetric, as well as a normal 3D, plus dynamic load balancing. It's a great code. So using that, we have, so all of those classes are in blastFoam. We haven't modified them other than to make them compatible with the newest OpenFoam versions. However, using that, we have created adaptive FE mesh, which is a modified version of their dynamic refined balance FE mesh. And it's really specific for blastFoam and kind of compressible flows in general. So what it is, it balances, it does AMR, and then so typically for the dynamic refine FE mesh, you have to provide a field which is used to refine the mesh, used to determine whether or not you need refinement. So instead of that, we use error estimators, and you have your choice of how you would like to estimate the error. So a couple of them, well, the three that we have are either you can use a modified density gradient, which looks at the density gradient. You can also look at the change across a face for a given field, so you can select that field, and then also the smoothness of a given field. So the exact refinement criteria you have to is determined by the user, but those are all, they provide some numerical, some number for the error, and then you can refine based on that. So other things, we have improved compatibility with castellated meshes from Snappy. So Snappy uses the octree refinement, which is what the standard hex 8 refinement uses. So for that reason, it's very easy to continue refinement of those. You can refine surfaces, and it will continue to refine those areas even after the fact, sorry. However, that can only be done for 3 dimensions. With 2D and 2D axisymmetric, it will break. But you can still use it with cut cells as long as it's all level 0. And then, so whether or not you use 2D axisymmetric, or 3D, that's all determined by the mesh, which is common to the original solver as well. And then, so lastly, based on the adaptive FE mesh as well, we have a moving adaptive FE mesh. So this is still experimental. Done some basic tests with it. It's not by no means 100% validated. But what this is, it includes everything that adaptive FE mesh has. So it has that balancing, it has the AMR, it has the error estimators. However, it also includes mesh movement. And I'll talk about this in a second. So we also have additional function objects. Some of them are specific to blast and compressible flows, and some of them are more general. So the blast specific ones, we have impulse, overpressure, dynamic pressure, speed of sound, and time of arrival. So impulse is just the integrated difference from a reference pressure over time. Overpressure is the difference between your current pressure and your atmospheric. Dynamic pressure is essentially your momentum contribution, or your kinetic energy, sorry. Speed of sound speed of sound. And then time of arrival is the time at which your maximum overpressure is reached. And then so some of the more general ones we have a write time list, which essentially what it does is you provide a list of times that you would like to write at, and it basically overwrites that write interval, and it'll write at that list of times. So it's useful when you have things like, you're doing a validation case and you need to write at some really weird time step. So you don't have to adjust your total or your global write interval just so you match that. You can just provide it here. And then lastly, we have field max. So what this is it stores the maximum value of a given field seen at every cell over all times. So this is useful if you want to see like what is the maximum overpressure I've seen, or what is the maximum impulse. It'll store that and track it. One thing to note, if you do use adaptive mesh refinement, as you unrefine, it'll take the volume average of cells, so you can actually see that decrease, and that's just because it's averaging all the cells that it's refining. Just a note. Okay, next we have the set refine fields utility. So this is, I think, my favorite little utility we have. So what it does is, if you're doing any sort of VOF solver or anything where you need to have, pretty big cells, and most of it, however, you need to have like a circle or a sphere well resolved when you start. It's very difficult to do. Basically, you have to rerun the calculation yourself. If your cell is too small, sometimes it won't even catch a cell, or if your area is too small, you might not even catch a cell and you just won't set anything. So what this utility does is it sets fields, and then it will refine, and then it will set fields again, and then it will refine and just slowly resolve that edge. You can also refine the internal cells of a cell set, and you can also refine the faces of a face set. So it's similar to how Snappy would refine a boundary. You can resolve a patch here or other face sets. We can also, one nice thing is you can resolve different cell sets at different levels. So if you have two spheres and you want one resolved to level 4 and you want one resolved to level 6, it won't resolve them both the same. It'll be different. Very similar to Snappy. And something else, you can also refine or define backup areas. So basically what this does is if you have a really small area that won't be caught by any, you can expand the area which it looks, and it will refine that additional area and then continue. And I'll show you why this is important when we go through our validation case. And then this also has compatibility with the 2D axisymmetric, and then the 3D meshes, or AMR as well. So you won't always refine in 3D. And then something that's specific to set refine fields, it's not really important in regular set fields. You can use a non-initial or non-uniform default field value. So this is useful if you have something like an atmosphere where you're going to have a gradient, but you want to set an individual section of that, and it'll set it, and then it'll replace whatever field you had with whatever the original value was, so that you update the refined fields correctly. Okay, so the last section here will be coupling with the precise solver or interface. So blastFoam is ready to be used with Precise's open foam adapter. So if you don't know what Precise is, it is a interface so that you can use different solvers, and it transfers the data between them. So for example, Calculix is a solid mechanics solver. That's what this was done using. So Calculix will solve the structure, which you can see is the flap down here. And then OpenFoam will solve the fluids, and Precise will send the mesh movement and the forces back and forth. So here we're going to be using the moving adaptive mesh class. So I'll play this for you. So you can see on the right here, we have the adaptive mesh. We also have the moving flap. A couple caveats with this, mostly due to, well, solely due to limitations on Precise. Currently, the interface between at which Precise passes information cannot change during the simulation. So for this reason, you have to protect boundaries, and basically this is just done by specifying protected patches and dynamic mesh dict. And this will also protect it from unrefining. So that means that if you have refined faces, it'll keep that. And you can also not currently use balancing, again, just because that would cause a change in that the boundary, which is not currently okay. Okay, so now I'm gonna just kind of very briefly go through some of the solvers that we have. So blastFoam is the main solver. It is, as I mentioned, set up to solve that 5-equation compressible system. However, it does handle more than that. So it's the single phase as well as a multi-phase solver. It includes all of the functionality presented. So this means we have the dynamic meshes, we have the improved AMR, we have moving meshes. And you can also include all of the function objects that I mentioned before without having to have that additional library addition like you typically do for normal OpenFoam. So it's just included. And in addition to the function objects mentioned, there's also a blastFoam sampling library. So the main benefit or extensions to this, so there's a slightly improved probe utility. So this will append to the end of existing probes. So if you're continuing a simulation, it will add on to wherever you're starting. So it'll load in the file and then it'll append from whatever time you're starting at. And then we have the option to actually move points inside the mesh if they're not there originally. So if you're barely outside the mesh and you're aware of this, and you just want to move the point inside the mesh to the closest cell, it'll do that. And then you can also, we've removed the problem where if you have a probe on a patch interface, it'll complain. Basically, it just removes that error that's printed, and it also removes the weird oscillations, they're not oscillations, but the weird steps you get in the other case, in the normal case. Next, we have the blast reacting foam. So as I mentioned, we don't currently have multi-species transport. So the way around this is to use the blast reacting foam. So it's a modified reacting foam solver. It uses the standard OpenFoam thermodynamic classes. So this means that you have the option for multi-species. You don't have all of the equations of state present in blastFoam. But you do have all of them from OpenFoam. Combustion models are enabled. So this means you can either solve all of the equations or you can use one of the more simplified combustion models. Multi-species transport, as I said, is there, and it's done using the ODE integration system and the Riemann flux that are used. So by default, it uses the Riemann flux scheme to transport all of the species. Yeah, so this is basically just sort of a way around that current limitation of not having reactions or multi-species or things like that in blastFoam. Next, we have blastFoam. So this is still experimental. We did some simple validation cases with it, but has not been extensively validated. So what this is it's a modified SciFoam solver. So this has unreacted and basically total thermodynamic contributions. It uses the ODE time integration system for energy of both the unreacted and reacted, or total and unreacted states. And it also uses the Riemann fluxes. And then this is, so what this is used for is deflagration to detonation transition cases. Basically, when you get large pressure buildups due to combustion, you want to be able to handle this in the fully compressible sense and not have the weakly compressible form, which is typically used in open foam. So it's useful for those kind of situations. And then lastly, we have our new solver, which is the Blast multi-region foam. So this is based on the conjugate heat transfer multi-region foam solver. Again, uses Riemann fluxes, it uses the ODE solver. For the fluid, the solid is still solved implicitly. However, it does use all of the blastFoam specific thermodynamic classes. So we have also updated all of the region coupling boundary conditions to use our thermodynamic classes. So this means things like convective heat transfer, radiation heat transfer have all been updated, and you can use those. It's been it's been very weakly validated. Just a couple test cases have been run, but it is there if you would like to try it. Okay, so running blastFoam. So the required files are very standard, pressure, density, temperature. And then if you're doing multi-phase, you have to provide volume fraction. The internal energy will be calculated from the pressure and density, or pressure and temperature, depending on which equation of state you use. So nothing weird there. Constant files, you have to provide a phase properties. So this is really the bulk of all the information. So you need your list of phases, and then you need your thermodynamic model variables. So this sort of has the standard thermodynamic properties inside of it. And then, as always, the dynamic mesh dict is optional. And then the turbulence properties is required only if the viscosity is not 0 for all of the phases. And then in the systems files, basically you just need control dict, FE schemes, and FE solutions, all of the normal files. Okay, so the case we're going to be going through is the Kingery-Bulmish equations. So what this is it's an experimentally fit equations. So these are very widely used in the blast community. Basically, it's a good way to get a good approximation on things like peak overpressure and peak impulse, as well as the time of arrival. So what we're going to be looking at is we're going to be looking at a hemispherical 10-kilogram charge of TNT on the ground. We're going to be doing a 2D axisymmetric wedge with adaptive mesh refinement. We have a 16 by 16 mesh with a mesh size of 0.32 meters. So for the adaptive mesh refinement, we're going to initialize everything with a maximum cell level of 6. And then when we're actually running, we're going to have a maximum cell level of 4. And we're going to be using the linear activation model. Okay, so this is quite a long file. It's split into 3 parts, so you can kind of see it all in one. So this is specifically the TNT section of that phase properties file. So at the top, you can see the phases, which is basically just the TNT and air. So it says we're going to be using a TNT phase and we're going to be using an air phase. These phases are needed to read in the variables from the initial conditions. So you need things like rho.TNT and rho.air. The TNT will be a detonating fluid. So you can see here, it's type detonating. And for this detonating fluid, we need both reactants and products defined. So the reactants are going to be your solid phase, and then the products are going to be your energetic explosive phase, or gaseous phase, sorry. So the reactants, we're going to pretend like we don't really know anything about this material. So we're just going to be using the simplified ideal gas model. It's really cheap to calculate. It's not really used, so it's fine to use this. we're going to be using a gamma of 1.29, which is just this omega plus 1. That's generally a good rule of thumb, I guess. We have the molecular weight for TNT, our transport properties, which is going to be in viscid. The thermodynamics, which is we're going to be using a constant CV value. Heat of formation here is going to be 0, just because we're adding it through our activation model, not through heat of formation. And that is the definition of the reactants. It's basically the same as the thermodynamic definition in open foam. And then for the products, again, we're going to be using constant transport, constant CV value. However, we're going to be using the JWL equation of state. So within the equations of state, we have our reference density, which is going to be 1,630 kilograms per meter cubed. And then we have our other model coefficients, A, B, R1, R2, and omega. And again, these are all very easy to find. They're very easy to find for most common materials and even variations of those materials. And then again, we have molecular weight, transport, and CV values. So then lastly here, we have the definition of our activation model. So we're going to be using the linear activation model. This E naught here again is the detonation pressure, if you will. It's given in units of pascals. That's what it's generally given in. So what it is the specific energy times the reference density. So we're going to be detonating it from the origin, and we're going to have a detonation velocity of about 7,000 meters per second. And then lastly here we have the residual density in alpha, which are basically just ensuring that you don't divide by small numbers. All right, so after the TNT, we need to define our air. So we're just going to be using an ideal gas with a gamma of 1.4. So the reason why we actually define our gamma and we don't use the molecular weight is mostly just because for compressible flows, generally you know your gamma. So that's why we do it that way. Yeah, everything else here is pretty standard. Again, in viscid, and we have our constant CV values. Next, we have our dynamic mesh dict. So this, again, is pretty standard. We're going to be using the adaptive FE mesh class, and then we're going to be using the modified density gradient for our air estimator. We're going to be refining every 3 steps. Next, we have this optional load balance dictionary. So by default, we have balancing turned on. The balance interval is 10 by default. The allowable imbalance is 20% by default. And then the method is that which you use to decompose or balance the mesh. So by default, it's whatever you specify in the decomposed pardict. However, if you have something like simple in the decomposed pardict, that's obviously not going to balance your load at all. So you can specify an alternative method here. Next, we have this lower refine level, which is the minimum value at which you will refine. And then we have our unrefined level. What I have found for density gradient, generally speaking, 0.01 is a pretty good number if you're looking to refine just about everything. If you want to resolve most stuff, but it's not crazy, 0.05 is a pretty good number. And then if you're just looking for something kind of quick, 0.1 is generally pretty good. Additionally, it's not included here, but you can also specify a time to begin unrefinement at. So this would be for something like it's going to take a little bit for your detonation wave to get to the first cell, but you don't want it to unrefine, so you can specify a later time to which to begin unrefining. One thing different than the standard dynamic refine FE mesh is that this buffer layer is here. So generally, that means that you have a protected layer where you cannot unrefine. What we actually do is we refine that buffer layer. And we do that because it allows it puts more space between the shock front and then the coarser cells, which are going to be in front. So what this means is you can take more steps between the refine interval and still maintain that resolution of the shock front. And then finally, we have the maximum refinement, which is the number of refinement levels it has. And then finally, do you want to write the cell level as a vol scalar field? Okay, next we have the FE schemes file. So most of this is very, very similar, specifically to row central foam. So the flux scheme, we're going to be using the AOSM Plus, but you can specify any of those presented. So the DDT schemes, we use this time integration selection here. The default really is not used. For the time integrator, we're going to be using the RK2 SSP. However, you can use any of the other ones. Personally, I think the RK2 SSP is the best balance between accuracy, stability, and performance. You have 2 steps, but it's still very stable. It's much more stable than Euler, but it doesn't cost nearly as much as, say, an RK4. You also have no storage, I believe. Next, we have the gradient schemes. So what this is used for is it's used for the limiters. So basically, you want to have a good estimation of your slopes or gradients for the limiters, and that'll tell you how much you need to limit. So we have found that the cell MD, specifically least squared 1, seems to work best. You can also use face MD limited, but that tends to be a little more diffuse. But it also gives more symmetric results if you do any sort of spherical charge. So in the divergence schemes here, you don't really have to specify any for the general solver. This is an example, though, if you were to use something like a pressure-based activation model, which we will not be using this, but it's just to show you. So this is the scheme you need to specify. And then we're going to be using the Riemann scheme. So when you use the Riemann scheme, you also have to specify the limiter for your lambda.tmt field, which you can see down here. So we're going to be using the cubic scheme. As I mentioned before, we have the option to use these higher order interpolation schemes without the major drawback of a greatly increased computational cost. There really is no noticeable difference between using a linear scheme and using a cubic scheme, which is really nice. So here we have to specify all of the limiters. Generally, it's best to keep these the same, but you do have the option. For vectors, you should use the V at the end of whatever scheme you're using. It basically just limits each component of that individually. And then if for whatever reason you miss one, it'll complain every time step or it'll fail. Well, it will fail, but it'll also complain every time step telling you which one you need. Next, so this isn't necessarily required. It's not required. These are just kind of a brief showcase of some of the function objects we have in here. So you can see we have our impulse, overpressure, maximum pressure and impulse, and then time of arrivals function objects used. So you can notice we don't have to include that libs and then whatever the library is. It's just naturally included. So we're going to be using impulse. We're going to have to provide a reference pressure for that and the overpressure. So the overpressure has the option to store it. So this means that it will not delete it as soon as it's calculated and written. And this is useful for things like storing the maximum or using it in other function objects, as well as probing, things like that. So this maximum pressure and impulse, we're going to be looking at the overpressure and the impulse fields. And then lastly, we have our time of arrival, which is basically, again, just going to store the time at which the peak pressure is reached. All right, so moving on to more simulation determined or initial condition setup, that kind of stuff. So this is going to be the set fields dict. So we're going to be using this with set refined fields. However, the set fields dict will work with set fields as well. So what you need is you need to specify the fields at which you are going to be looking for refinement in. So basically this will track, for our case, it'll be alpha.tnt, and it'll track where there's changes over faces in alpha.tnt, and it'll refine those. So we're going to be specifying the number of buffer layers. Again, this is the number of basically cushion cells that occur around the areas of refinement. And then we're going to need to specify our default field values. So this is much more important for set refined fields than it is for set fields. Basically what will happen if you do not, it'll just continue to set over top. So it will only refine whatever your first cell is, which isn't what you want. So the regions, pretty standard. You know, you have all your normal cell sets and face sets. So here we're going to be specifying a sphere with a center at the origin and a radius of 0.13. So as I'll show you in a minute, that actually wouldn't set any cells at all. So what we want to do is we want to specify a backup region of 1 meter radius. So this will never set the actual radius of your whatever you're setting to 1. It's only used for refinement. So it's not like you're going to have to, if you're looking at 10 kilograms of TNT and you set a backup area that's a meter, it's not going to set, you know, way more than that. It'll always only set to whatever radius you actually specify here, or whatever units you specify here. So here we have the option to refine the internal cells as well as the external, as well as the boundary cells. So we're going to be doing that, and we're going to be refining it up to level 6. And then we're going to be setting the field values of alpha.tnt to 1. So a couple things. So if you just want to refine an area, say you just want to refine the cell and that's it, you don't have to include this field values here. You can just set it, and it'll just refine those cells and it'll stay the same. For face sets, this refine internal becomes refine faces, and that'll basically just refine whatever face sets you provide, or the cells around whatever face sets you provide. So this is what our initial conditions look like. So what the original, you can see that we have a very large original or base mesh, and this cell center where the charge is actually set would not have been caught by the cell volume we're looking at. So you would have set it, and that it would have said, okay, I haven't changed, so I'm gonna exit now. You wouldn't have gotten anything. So what that backup does is it creates a bigger region in which you can look to refine, and it'll find the cells in that region, and then it'll refine the ones that are necessary. Okay. So these are just the results. Sorry, I don't have the AMR plots on here. So we're looking at overpressure here. So this is the output of one of the function objects, and we also have our volume fraction here. So at the bottom, you can see our comparisons with the Kingley-Bolnish equations. We match fairly well, aside from this little dip and impulse here. But fairly good, generally speaking. And I should note, well, so additional validation cases. So all of the cases presented here are available in blastFoam. You can run them all yourself. You can make sure that, you know, what I'm saying is correct. We provide plots that, you know, we receive. So what you're seeing here, if you run them and they're not, you should let us know, because something must have happened. So we're going to move on to some additional validation cases now. We're going to go through a single phase selection and then a multi-phase selection. So these are generally speaking, pretty standard, at least for the single phase. And then for the multi-phase, we have some, I guess, more non-standard cases. So the first case here, we have the standard SOD shock tube. This is from SOD 1978. So we start with a density of 1 on the left and a pressure of 1. And then on the right, we have a density of 0.125 and a pressure of 0.1. So you can see we match very well. We capture the shocks quite well. It's what you'd expect to see. So we have pressure, velocity, and density here. Next, we have a set of blast wave in both 2D and 3D. So what this is, it's initialized using a point energy pill. So basically you have a very, very small volume initialized with some energy. We use the pressure, and then you allow it to expand out. So we use an ideal gas here. And then this is compared to the work of Sedov from 1959. So it's essentially an exact solution to this equation. So 2D and 3D, you can see we match quite well. This peak is incredibly hard to get just because it's exact. So this is the initial conditions for the pressure. Density is uniform. E here is 1, and then the delta R is just the initial, the grid spacing, or the radius of your initial pill, essentially. And then D is the number of dimensions. So we have a different energy or different pressure initialized for 2D and 3D. Next, we have a 2D Riemann problem. So this here, you can see we have basically quadrants of different densities and pressures. This is the density field. You can see we match pretty well with the original Lax et al. From 98. This video here is a much more refined version, as you can see from all those little vortices forming, but just kind of to show you what is going on. So those were the single phase simulations. Now we're moving on to the 2-phase / multi-phase stuff. So this here is going to be a 2-fluid shock tube. It uses a stiffened gas and a van der Waals equation of state. So this is compared to the work of Zhang from 2011. So this is what really most of the original blastFoam work was based on. So from equations of state to the pressure blending, if you will, speed of sound, that kind of stuff. It was mostly all based on this work. So this was one of the simple validation cases we did to originally test the code. So here we start with a fluid density of 1,000 on the left, volume fraction of fluid of 1, and then the pressure of 1 e to the 9th. And then on the right, we have a gas phase. So we have no fluid, all gas, and we have a density of 50 and a pressure of 1 e to the 5. Again, you can see we match fairly well. Exactly what this little bump is, I have no idea. It's always been there. It never goes away. It's the only case it happens with, but all of their other results match very well. Lastly, we have a collection of rate stick simulations. So what this is basically we hit the bottom with some velocity, we allow it to compress, and then we watch how the detonation velocity, we look at what the detonation velocity is. So this is done using the JWL++ model. What it is, it's the Murnaghan equation of state for the solid phase, and then the JWL for the gas phase. This is from Sowers et al. 2000. We use a pressure-based activation model for this. This is really a validation of that. And then our results are compared to the work of Galicki et al. From 2007. So in the top right here, you can see ours is in the red. Blue is experimental work, and then black is previous simulation work. So we match very well with the experiments. We're a little bit different than the simulations. But what this is, it's a plot of the inverse radius versus the detonation velocity. So this video here is a selection of, I believe it's the center point. It's a 12.5 millimeter radius. And you can see it begins to compress. It doesn't activate right away, but once the pressure becomes high enough, it causes a positive feedback loop, and you get that kind of constant detonation velocity that occurs. And as you can see, that the radius has a big impact on the detonation velocity. It's half between a infinite radius and a radius of, I think it's 6 millimeters. Okay. So, brief summary. So blastFoam 3.5 will be released later today. Really what it includes, it wasn't enough to constitute a major release, such as version 4. It was mostly just improvements to everything that's already been there. So it's restructuring of thermo classes. We added the moving meshes, so that coupling with precise. We have the improved AMR with the work from Rettmeyer 2019. We have better support of castellated snapping meshes. We've been using it quite a bit in some of our more complex cases for some clients, and it's been working very well. And then, really just some additional decoupling of classes. So this is things like the flux schemes, as well as some more solver-specific compressible systems. Things like the reacting system specifically for reacting or blast reacting foam. It'll make it much easier to incorporate some of the really big changes in the dev branch currently. So then looking forward, we have blastFoam 4, which is going to plan for release in late summer, early fall, really with a focus on particles. So this is what a lot of my PhD was particles, dispersed phase, that kind of stuff. So specifically, the main addition here is going to be the kinetic theory-based Euler-Euler method. The really big thing about this is we've included multiple particle sizes. So currently, even reacting Euler foam does not allow you to select multiple particle sizes. We will have that. They will be correctly handled. So the interaction between particles, the interaction as the particle phases, total packing limits, that kind of stuff, it's all handled. However, it'll be in the fully compressible sense. So it's very exciting. We'll also have Lagrangian solvers. So this is similar to the parcel foam, reacting parcel foam. So we'll have coupling with drag and as well as heat transfer. And that goes for the Euler-Euler method as well. And then we will also be coupling to OpenQBMM. So this will include things, particle size distributions. So this is things like aggregation and coalescence, breakup, nucleation, growth, all of that. So this will be for inertial and non-inertial particles. And then basically from that, we'll have some additional activation models that are, more size dependent, things like aluminum combustion, that can be used for things like aluminum combustion, stuff like that. Okay, so resources. So if you need help, the user guide is pretty good. It includes, I hope, everything in the code that you can do. It's a nice, concise overview of the theory, the equations, sort of how to use it. A lot of the sections have entries as far as like what the dictionary should look like, and then kind of how to use them. If you're interested in any sort of training, email us, info@synthetictechnologies.com. We do custom and private workshops and training. If you find any bugs in the code, it's always nice to know people are using the code. Submit them to our GitHub page. And then, if you like what you've heard and you're like, I have some specific application that I want, you can always ask us to implement something. We're always looking for community suggestions, community involvement. If you have something you want to commit, let us know. Here are our references, and then questions. I don't know how questions are typically done.
Thanks, Jeff. Let's jump in real quick and go over. So you can do questions in the chat. There's also already a question in the Whova Q&A. If you would like to put your question there instead, that makes it stick around and be permanent, I guess. I don't know how long it stays up. So we'll deal with that question first. So the question from the Whova is, can blastFoam work out of the box for rotating detonation engine simulations, both in Euler and Navier-Stokes framework?
We have gotten this question a lot. So I am not, we've talked about setting up a case for it, basically from my looking at it. I would assume you need some sort of reference frame that is currently not in blastFoam. It's been on my radar, but other than that, there should be no limitations as to why you can't. I don't trust myself enough to set up a case. It seems very like you need a lot of expertise, and I certainly don't have that, so I've kind of stayed away from it. But it should be getting there. You can certainly try. If you can, let us know. It'd be very useful to know. Most everything should be there, though. In regards to the SciU compressible system, basically, so the code we originally did or used for deflagration to detonation transition, they had that limit temperature. Basically, when you have no more unburnt material, it does go very low. It's not used, I don't believe, but it does fall below that temperature and goes to zero, basically, because there's nothing there. Or at least that was the experience I had. As far as using blastFoam or blastFoam for the deflagration, I would say that would be the best bet. Actually, we do need to add the moving meshes and everything else to that. But so blastFoam isn't really set up for combustion. All of the energy addition models are basically just the simplified models, and it's primarily just for detonation. It's not at all for things like combustion. So it really isn't applicable to that. So I would say blastFoam, or I mean, if you really want to go crazy, you could use the blast reacting foam and just solve everything. But yeah, I'd say you need something like that. So the moving detonating pellets, we currently do not have anything like that. That'll hopefully be something, well, actually that's not true. I guess if you initialized a solid phase and had it moving with some initial velocity, you could do it like that. But we currently don't have any sort of immersed boundary or anything like that where you could really maintain that shape. I would say the best thing would probably be when the particles come out. You can either do that as like a granular type phase and have some energy addition from that, or do it as a Lagrangian. But as far as actually like having that transition from a solid to a gas or something, we currently can't handle that. So the next two questions are kind of go well together. So the blast reacting foam, really what it does is it's meant to solve all of the chemistry. So again, blastFoam can't do that. We don't have the mixtures set up. However, OpenFoam does do that very well. So we basically just wanted to utilize that and use it specifically in the very compressible sense where you have these explicit fluxes, you have ODE integration. Currently, all of the species are not transported with the ODE solver. They're just using the final fluxes given from the ODE solver. But the heat addition just comes from the reaction. So it's exactly the same as the standard reacting foam. So you have that, I believe it's Q dot, which is added to the energy equation. And that just comes from the chemistry or the combustion model. And that would be how I would suggest solving a detonation with detailed chemistry as well. Does that make sense? Yeah, so the blast reacting foam, I would say it's the more advanced version of, I mean, as blast or reacting foam is to Styrofoam, it's the more DNS type version of that. So Styrofoam makes some simplifications. It uses the reaction progress variables. And basically the same things apply again. It's really just the time integration and the flux schemes. If you're doing any sort of DDT, I would definitely recommend Styrofoam. It'll be much faster and much easier to use. Yeah, it's much faster. You don't have to solve the chemistry ODEs or anything like that.
Jumping in again, we did have a question that we missed at the beginning of the Q&A from Justin. He asks if you have any recommendations about coupling codes to blastFoam to demonstrate damage on structures mid blasts, or is this something that is handled natively?
So we do not do structural damage natively. So this would be what Precise would be used for. So we had done a workshop and someone had told us about this and I had no idea it existed and found out it worked pretty well. So I have a case it's not currently in the release version. However, I'll probably add it sometime soon. Basically we're using Calculix currently. I don't really know how to use it. I'm just using the case that was set up in their tutorials. So you'd have to, and I know we've talked to some other groups who are looking at coupling their code with Precise for structural analysis. So you would have to basically couple it using some method. Precise is probably the easiest. And so it'll pass the loads and then you can evaluate the structural damage within that structural mechanics solver. However, the fluid side, we are set up to handle, that moving mesh and all of that.
Vishal added at the end, asking if you could add a tutorial case for blast reacting foam.
Yeah, I think there is one now currently. Mostly the reason it has not been added yet is just because I don't really haven't thought of any good tutorial cases that would illustrate the combustion well. Originally there was some of the, just the reacting foam case in there, but it was just so slow and for no reason, just because of the time step on the CFL condition. I believe there is a very simple blast reacting foam in there for like an oblique wedge though, or oblique shock, sorry, that you can kind of use, and it's not multi-species or anything like that, but the rest of it's just done using the standard as you would usually do for reacting foam.
All right, I think we have time for one more question right at the end here, if anybody wants to jump in. And if not, I guess we can go ahead and call it there. Thanks again, Jeff.
Thank you guys for coming.